Okay, the next couple of lectures in the class concentrate on distribution functions. And the first kind of distribution that we want to talk about is the binomial distribution. Now, when doing probability and statistics, one thing that you have to keep in mind is that you always want the distribution you use to match the physical problem that you're modeling. So, in a binomial distribution, it's an either-or kind of problem, or a yes-no kind of problem, or a does it happen, does it not happen. So we're going to define an event A, capital A, and we're going to say that we have n independent trials, and what we're interested in is how many times does event A happen in n independent trials. Remembering that the only options are either A happens or it doesn't happen. So in each trial, each event A is going to have the probability little p. So if A does not occur, the probability that A does not occur will be 1 minus p, which we'll call little q. So in n trials, this random variable that we're interested in is capital X. And capital X is going to be the number of times that event A occurs in little n trials. So obviously A could not occur at all, meaning that X is 0, or A could occur every time, meaning that X is n. And so we want to determine those corresponding probabilities. So we're going to define lowercase x as the number of times that A occurs. So A is going to occur in X trials, meaning in n minus X trials, the remaining trials, it's not going to occur. So basically we have A occurring X times, and then the complement of A, which we'll call B, occurring n minus X times. So A occurs X times, and it doesn't occur the rest of the time. Now, it's important in the binomial distribution to assume that the probabilities, at least in how we're going to discuss it, to assume that the trials are independent. In other words, they don't influence one another. So if we then want to calculate this, we have X number of multiplied probabilities that A will occur, and n minus X that A will not occur. And so let's go back and get the terminology. Basically, we want the probability that we will have X occurrences of A and n minus X occurrences of B. So that's what we're actually modeling with this equation. So we take little p, which is the probability that A occurs, and we multiply it together X times, and then we take little q and we multiply it together n minus X times, and what we get is p to the X, q to the n minus X. So once again, p to the X, q to the n minus X is the probability that the event will occur X times, and the complement of the event will occur n minus X times. So now we go back to permutation theory, and we're going to say we have n things. So we have n possible outcomes of the n trials, and we have two classes. Class 1 is the number of A's, so that'll be n1, and class 2 is the number of times B occurs, so that'll be n minus X. So we have X occurrences of A, we have n minus X occurrences of B. So if we want to get the number of permutations of that, that's basically n factorial over x factorial times n minus x factorial, written in shorthand notation as bracket of n over x. So if you then want to find the probability that the number of times x occurs is little x, so basically finding that as a function of x, you say f of x is, and then here's our permutation formula, and here is our probability formula. So the distribution of x with this probability function, so this is our probability function because remember it's coming out as a function of x, is referred to as the binomial distribution or the Bernoulli distribution. The occurrence of A is called the success, and the non-occurrence of A is called failure, and that's just statistical language. So figure 517 shows some typical results. This is the probability function for the binomial distribution for n equals 5 and various values of p. Now let's remember once again what little p is. So we'll go back a couple of slides to where little p is defined. So little p is the probability per trial that A has occurred. So if the probability of A occurring in a trial is 0.1, then the probability function among 5 trials looks like this. If it's 0.2, it looks like this. If it's 0.5, it looks like this. So I want to stop on 0.5 for a moment. Notice here that the second and sort of the middle trials are where you get your peak value of the probability function. Now, if you want numerical values, you can get those in Table 5, Table A5. So we could find the mean of a binomial distribution as n times p, and the variance as n times p times q. Now, if p is equal to q is equal to 1/2, we get a mean of n over 2, and we get a variance of n over 4, and the probability function reduces to the permutation formula times 1/2 to the nth power, where n is the number of trials. So the binomial distribution can be useful. Now, we're going to talk a little bit later about the mean of a distribution and the variance of a distribution. In the past, we have discussed the mean of a set of sample data and the variance of a set of sample data or population data. When a population is modeled by a distribution, the symbols for mean and variance are sometimes different depending on the source, and so this mu is indicating that we have a distribution that represents a sample of a population, as is sigma squared. So here's just an example of using the binomial distribution, calculating the probability of obtaining at least 2 6s in rolling a fair die 4 times. So the number of events is 4. The number of possible outcomes is 2. The probability that we would get a 6 is 1/6. So here's our number of permutations, 4 over 2. And note that it says at least 2 6. So we want, if we do 4 different trials, we'll first of all want the probability that we get 2 6s, then we would want the probability that we would get 3 6s, and then we would want the probability that we would get 4 6s. So each of those is a separate case. So if we look first at the function for getting 2 6s, we would have 4 trials, 2 outcomes, a 1/6 probability of getting a 6, a 5/6 probability of getting a not 6. Each would be squared because we're assuming this is the case where we got 2 6s. If we assume we get 3 6s, we have 4 trials, 6 occurs 3 times. We would then have 1/6 to the power 3, and we would have 5/6, which is the complement of 1/6 to the power 1, and so on. With the last case, this 5/6 goes to the power 0. So that then gives you an overall probability of 13.2%. So that's the binomial distribution. The Poisson distribution is basically a discrete distribution that has infinitely many possible values. And so the probability function is represented as followed, where mu is the mean and sigma is the variance. So the Poisson distribution has mu to the x over x factorial e to the minus mu. The Poisson distribution is used to describe discrete distributions that have an infinite number of values. If you let n go to infinity and p go to 0, then this is basically a limiting case of the binomial distribution. So if we want to look here, here's the probability function for the Poisson distribution with various values of mu, just shown for different cases.